have any radioactive waste. So this is great. Why don't we have fusion plants? It's a problem. The way I controlled this was by absorbing the neutrons. The way this works in the sun, that we talked about last time, the sun is huge. There's a lot of gravity. All that gravity from the sun, from all that mass that's in the sun, does the work of squeezing these things together. I don't have that much gravity here. I have to squeeze them together some other way. I need some way to get these protons to overcome this repulsion between the two positive charges so I can get to where the strong force takes over. So that's a tremendous amount of squeezing. How do I do that? The way I do that is by having these protons zoom around really, 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 really fast. So in this case, the neutrons that come off are slow. They have to be slow because they have to hit the U-235 and stick to it enough for it to break apart. So the neutrons here, they're not really shooting off. They're kind of just bumbling around. In this case, I need these protons to be moving fast. Now, the speed of a particle is what we call temperature. Hot is things jiggling around really quickly. Cold is things moving around very slowly. That's what temperature is. Temperature is nothing more than a measure of how fast the particles are moving. If the particles are complicated, there's also a component to how fast they're spinning. If it's like a dumbbell spinning around, that's part of temperature. But motion, the speed of motion, is what we call temperature. So these are cold neutrons, and I need really hot protons here. If these things are hot, if they're moving around fast enough, they can actually move, that energy of moving around can be enough to overcome this positive repulsion long enough for the strong force to take over. Without the strong force, they would come, they'd just get closer, they'd bounce off again. But because I have the strong force, if I get past this threshold, if I get them close enough, then they'll stick together, and I'll get the energy out. And I do that by having them move fast enough to do that. So I need protons that are moving around really, really fast, they're really, really hot. This is where you've heard the word thermonuclear bomb, thermonuclear war, any of that kind of stuff. Thermo is heat, temperature. This is thermonuclear fusion. This is not thermonuclear, this is fission. It's not thermal in that sense, it's not hot. So thermonuclear fusion is how I do this. I need these protons to move around really fast, and then I get a bunch of energy out. So mostly what comes out of this, I'll have some helium that happens to be sitting here, but I'll also have these photons that come out. Lots of heat, lots of energy. That energy goes into the next set of protons I have and moves them fast enough to be able to overcome this barrier. And that keeps happening again and again. So I have another chain reaction. But in this case, the chain reaction was neutrons. If I absorb neutrons, I can stop the chain reaction. In this case, the chain reaction is just the energy that comes off. It's the heat. I don't have anything that can absorb heat and dissipate it or get it out of the way on this kind of scale. So what happens is that heat is what causes the chain reaction, which causes more heat, which causes the next two protons to fuse together. And I have, again, a chain reaction, but no way to slow it down and no way to stop it. So fusion is great because it would have these advantages of not having waste products. The waste products is essentially helium, not a lot of radioactivity left over. It's great because I could use any material. I can use water as the material. I just need to get hydrogen, which is easy. The problem is I can't stop it once it starts. So if I build a fusion reactor and I get it going and I get enough heat off there to keep it going, it's going to run away from me. I can't absorb it. I don't have these carbon rods that I can put in to slow it down or stop it. And so I can't make a power plant. I can make a bomb because then I just need enough stuff there, but I can't make a power plant. To make the bomb, I need to get the heat in there in the first place. So the way I do that is I build one of these, and I put it next to one of these, and this generates enough heat that this can get started, and then this takes over. And you don't really even notice this because this is way bigger. Much more energy is released in this case. So I can make a bomb with it, and that's great, if you're into that sort of thing. But what I can't do is make a power plant out of this using the same kind of technique here. So how do we make fusion power plants? What are people working on? There's a couple different ways to do it. What it basically results in is a pellet stove, where I have the fire going in the middle, and I take little teeny amounts of this, not enough to make a bomb, but just enough to keep it going, and I drop in a pellet at a time. And there's lots of different ways people try to do this, but essentially it's making little pellets of not quite big enough fusion bombs, and dropping them in a little at a time, and then if I want to stop it, I just stop dropping the pellets and it burns out. I'd have to start it again somehow, that would be difficult. I don't want to start it with having to blow up atomic bombs all the time. So a lot of the work is figuring out how to make something hot enough to get this started. They use lasers for that. There's something called the NIF, the National Ignition Facility, where they get all the biggest lasers in the world and they point them all at one spot just to get something hot enough, and then they drop their pellets into that spot. There's other ways to try to control this with magnetism, because these things are charged, so maybe with a magnetic confinement I can keep it in one place and stop stuff from escaping or growing and do a little bit at a time. That's the tokamak, or the stuff that goes on in Princeton. Some of these things in principle can work. The problem is being able to get more energy out than you put in. But in general, it's a much, much more complicated problem to figure out how to solve.
Time magazine just had a cover article on fusion plans, and I won't pretend to have understood it all, but it seemed that the scientists were a little bit more optimistic that they can get there this time. Do you have an opinion?
The public science press is the mechanism by which scientists get Congress to fund them to continue their work. So if you, it's a little hard now that there's the internet. If you look at some headline and you search for that headline, you will find that headline repeated whatever the interim period of people's memory is, or new Congresses, or whatever it is. Now, which is not to say that the work is not valuable and true, but most of what you're going to read in the public press is, wow, we solved it, or we're this close, or this, if we just had a little bit more, we could do a little bit more. And that's when new machines get built is when we have successful people making those arguments and writing those stories. Jane.
So given the relative simplicity of the science,
right,
does it surprise you that more countries are not, don't have nuclear capability?
No. The challenge is getting the material, getting uranium.
And it's costly, is that?
It's hard, there's not that much of it, and it's not pure. So you have to either purify it or you have to make it. So to purify it, that's a major job, which is what you need these tens of thousands of centrifuges for. You have to get the raw material, which is not impossible to find, but it's not that prevalent. You have to dig it out of the ground, you have to get it to where it needs to be. If you're trying to do this covertly, you need to be able to hide the fact you're doing that, which is extremely difficult because the stuff is emitting all kinds of particles. I mean, it's naturally radioactive. We have stuff's coming off it, which means it's not that hard to find. It's not that hard to see if somebody's doing something with it. And then you have to purify it. And that purification process is not that easy. It's a mechanical process. I'm trying to separate something that weighs 235 from something that weighs 238 by spinning it around real fast. And that mass difference, that weight difference is not very much. So it's hard to do, and it takes a long time. So I have to get the material, I have to purify it, and those are long steps. The alternative path, which is the path that all developed countries, all more sophisticated approaches, is we don't use uranium anymore, we use plutonium. The reason primarily is we can make it. You put it in a reactor, which is essentially an environment like where I have all this 235 together, neutrons are going. There's other different kinds of reactions that I can have. And a reactor is just a place where I can have these processes going that will sustain themselves and be controllable. A power reactor is a reactor that's designed so that it generates heat. But there are other reactors that we use to generate all kinds of other materials. All the stuff that you need for medical approaches when they inject you with things and these little radioactive chemicals that go through you and make imaging for PET scans or all that. Those are all made in reactors that are designed just to manufacture different kinds of things that don't occur naturally. And so that's the way we would do it now if we were still making new ones, is with these reactors making plutonium. So you see there's parallel development paths in any country that's attempting to get themselves a bomb. One is to try to do this purification process, and the other is to make a reactor. In a way, making a reactor is easier if you have to do it from scratch because it's stuff you can build. Making these centrifuges is very difficult because they have to spin very quickly, so you need very precise manufacturing capability. So nobody makes their own. You buy them from somebody who does make them and who knows how to do this kind of thing. Because you get something that spins very, very quickly, it's very easy for something to go very wrong very quickly, which happened a couple of years ago. You remember all the centrifuges were self-destructed from some magical plug that got in there somehow. And that's possible because these things have to be balanced so precisely and work so easily. It's not an easy thing to do in order to make the fission bomb happen, especially if you want more than one, and especially if you've got to move it somewhere. If all I want to do is build it right here, then that's not so hard to do. I just got to get the stuff, make a big pile. If I want to put this into a device that I can move somewhere else and then have it blow up where I want it to blow up, that's a much more, and when I want it to blow up, that's a much more challenging problem. There's a lot of more engineering there. So, that's why everybody who really wants one of these things and can do it probably has it. But it's hard for somebody to get started new. It takes a long time. But the technology is not really where your problem is.
Back to fission for a second. I just want to understand a couple of things. When you say that they're adding neutrons to the uranium, is that what we read about as enriching uranium?
The enriching uranium is the separating out the two kinds of uranium, the 235 from the 238. So if I dig up a thing, it's like 95% more than that. It's mostly 238, and enriching it is increasing the percentage of 235 that's in there, so that the reaction can carry on without the 238 absorbing the neutrons.
And when we hear about spent fuel rods, is that the carbon that is...
No, it's not the carbon. It's when the reaction happens, the uranium-235 breaks apart into pieces. That's the fission.
Okay.
Those leftover pieces, that's the spent fuel.
Oh.
And that stuff is still radioactive, but not useful to anybody. So there's things you can do with it, but there's no way to get rid of it. That's the spent fuel.
Couldn't you use fusion for space travel? Like, you want to send some kind of spacecraft to one of the outer planets. You get a lot of energy. You don't have to keep it going. You just want to push.
Well, you have to start it somehow,
Yeah.
and then you got to keep going. So that's the pellet stove idea is the same thing. The idea is you get someplace where it's hot enough, and you keep just dropping a pellet at a time. But it doesn't. There's nothing in space that changes the fundamental problem you had in a power plant. You still don't want your rocket to blow up, and if you can't have it run away. And that controllability, being able to pace how fast it happens, is the trick. And the pellet stove is really the only real way to do that at this point. Right.
And then a dirty bomb is what? Just impure.
A dirty bomb is a dirty bomb is not a bomb it's not a nuclear bomb.
Okay.
I take a bunch of radioactive stuff, which could be anything. It could be spent fuel. It could be something I dug out of the ground. Doesn't matter. You go to a hospital and collect all that stuff for the PET scans. Make a pile of it, and then spray it around with a water gun. It's nothing special.
So just a really simple concept and a phrase we've heard all our lives, like a Geiger counter.
Right.
Is that like, what does that do, and is that still a concept in use?
Yes.
It seems like an old...
That's on the detector side of things, which we're about to talk about. There's different ways as these things come out, we need to measure them. When we get into the experimental stuff. That's where I have to start making devices that can count these things and see them, and that's what detectors are. They won't work.
Let me ask you about why we don't see or have more nuclear power plants, and why does it take so long to build? Why is it so expensive? Is it all just politics?
It's the politics of fear. It's that nuclear is, if I say nuclear, everybody thinks either Hiroshima or 3 Mile Island, and they panic, and they don't want that anywhere near them. They're way safer from a public health perspective than coal power plants, which are killing tens of thousands of people just from the pollution. The difference is that with a nuclear power plant, even if there is a problem, that problem is localized, whereas with anything else that we do, the problem is spread out over everywhere it's in the air. But the fundamental challenge is just this idea that if something is nuclear, it's invisible and scary and dangerous, and it's associated with bombs, and it's associated with meltdowns and China syndrome and all this kind of stuff. And so people don't want it for that. What that does also is it means that new designs for power plants are hard to get accepted. Because if we have a design that was used in the 50s, then that's a officially proven design. And so people will tolerate a power plant from the 50s or 60s. What people won't do, though, is think, there's a new design, that's unproven, we can't have it, and so all of the power plants that are online now are designs from the 60s. We could do much, much better and much safer, but no one will because it's you just can't get that new design in. But it's a political problem.
Follow on the same thing. You have people building plants that are being put into aircraft carriers and things like that.
Right.
Presumably those are newer designs.
Those are
You take that and build smaller things, power in smaller areas. That the power system is designed.
Sure. The difference there is if you're the Army, you can do whatever you want. Because everyone who works for you and lives around you, you own. And there's unfortunate histories of what the military has done with the people they own, what we now call warfighters, soldiers and sailors. But But they have that control, and that's why they are able to do it. So the designs do exist, and they are proven in some sense, but getting something built here is not easy to do. So where we, let's see, we talked last time about some of these guys. One thing I wanted to point out is that these dates here of when they're winning these things are becoming increasingly close to now. I still think of it as being about 90-something, so this seems very recent to me. But a lot of these guys are still in play. Most of them are still alive or were alive in recent memory. A lot of the work that was done during the time that I was working actively in the field here. Hans Beta would come and talk periodically, and all these guys would move around. Monelson here, what he did when he got the prize for it in '75 was nuclear shapes and shells, collective versus single particle, and that's the subject of my thesis work. What we have here, so the nucleus can be deformed. So as I keep adding neutrons or do other things, it will start changing shape. And I have a few different kinds of shapes. There's a more spherical shape, which is the middle. I have what's called a perlate shape, which is more the jelly bean. I have the oblate shape, which is a more pancake kind of thing. So those are the basic shapes. These are all collective shapes. And then I have single particle shapes, where instead of having the whole thing deform, I can take a piece off and have it be kind of spinning around or circulating in some way. 2 or 3 neutrons, a proton, something like that. Kind of detaches from the main body of the nucleus and just starts moving around. Still very, very close, much, much closer than the electrons. But I have these 2 different ways now. I can change the shape of something, or I can move some of the parts off of it as I need to have an excitation in some way. So, experimental nuclear structure. This is all called nuclear structure physics. But I want to do an experiment. I want to see what these shapes are. I need to get a nucleus. I need to add some energy to it somehow to excite it. Watch it decay and measure it, and then do it again with a different nucleus so I can see what changed. In atomic physics, part of what we reviewed that at the beginning, I have an atom. It has the electron around it. I add energy to it, usually from a photon coming in. I go into a different shell. I watch it come back down. It emits a photon, and I measure that, and that's everything we've been talking about in the first and most of the second class. In this case, I'm doing the same thing. I'm following the same analogy, except I'm doing it with a nucleus. And this is becomes a harder thing to conceptualize, which is why we started with atomic physics. Now, when I have my nucleus here, and I add energy to it, I can do a couple different things. That energy can go a couple different places. I have the concept of shells, the same as I had in atomic physics, where I have a ground state, and then I have these excited states. And I can add energy, move up to a state, and then have it decay, and come off with a photon. This was the same picture that we had in an atom. The difference is what the picture looks like here, and how complex this is. In an atom, all I'm really doing is taking an electron, moving it to a higher shell, moving it down to a lower shell. It's fairly simple. When I get to a nucleus, there are lots of these shells all over the place. And they can be slightly different energies from each other. And I can go diagonally between them and up and down all over the place. And that's because instead of just having the ability to move an electron in and out, I can squeeze the shape, I can take one of these guys and start having it circle around this way. All kinds of stuff happens. So why is this relevant? Why is this important? Why bother with any of this nuclear physics stuff? And the reason is because it goes back to the strong force. I had the strong force, which I said is able to, wants to keep these things together, wants to keep the protons together, the neutrons together, and fight the electromagnetic force. The strong force really manifests itself in 2 different regions, 2 different ways. So I have one proton here and one proton here, and I have my strong force that keeps them together. But we talked a little bit about the inside of the proton, where I have quarks, which for the moment I'm going to draw like this. 2 up quarks and down quark. These things are charged. They're all, the net charge is positive. So I have plus 2/3, plus 2/3, minus a third charge here. So this thing wants to explode. This thing doesn't want to stick together either. And so I have stuff called glue that's in here, these gluons. And the gluons keep it together. The strong force is what's keeping this thing together. When we talk about the strong force most of the time, this is the strong force. And when we say we understand the strong force, this is what we understand. That's mostly confined within the proton. One of the major areas of particle physics and nucleon physics is the confinement problem. Why these things even stay together in the first place, and exactly mathematically how that works. because we'll get to a point where we see how complicated that picture really is, but that picture is well understood. So what happens though is that some of this, that explains why the proton stays together, but it doesn't tell me how these things stay together, how I get a strong force outside of this. What happens is that some of these gluons leak. This is not a well-defined boundary, it's kind of fuzzy. And that fuzzy boundary gives me what's called the residual strong force. So the strong force we talk about, that's really going on in here. The residual strong force is whatever's left over based on what the structure inside the proton is. I just have this extra glue hanging around. That's not that well characterized. It's not that well understood. And it's relatively straightforward still if I have 2 protons, 2 neutrons, but when I have 10, 50, 100, 250, 300 more, there's no way we have that we can calculate how that works, what this residual strong force does when I have a big ball of neutrons and protons. So I don't have a theory that says what can happen. I don't have a theory that tells me what atoms should be stable. I don't have a theory that tells me what's the biggest atom I can make, what's the biggest nucleus I can make. I don't have a theory that tells me how many neutrons I'm allowed to have. I can have those theories over very short areas of the periodic table or of the chart of nuclei, but I don't have a global theory for the whole thing. We don't really understand that. And that's going to be related in some way to what the shape of the nucleus is. So the purpose of doing nuclear structure physics is to try to figure out what this strong force is. Now it's great and exciting and fun to learn about the inside of this, but the practical application of a lot of these things, most of what we interact with, is not going on inside a proton. You want to know how the universe began, that's important. And again, that's on the sexy side of that chart that I showed at the beginning between the practical and the sexy. But if I want to know anything useful in terms of technology or anything I'm actually going to interact with, that's where I need to know what the nucleus really is and how it's put together. And that theory is not well developed, and that's why we still have nuclear structure physics. So I need to get my nucleus, add energy to it. So one way that happens is by changing the shell that I'm in. I mean, you have to think of the shell by analogy because there aren't really shells in these things. The other thing I can do is start spinning. Once I have changed the shape, and I have something that looks like this. This is exaggerated. And I've got my charges in here, and I start spinning this around and around and around. This is going to make a magnetic field come out. Because if a charge is moving electricity, a moving charge is electricity, and electricity always generates a magnetic field. So I'm going to have a magnetic field that comes off this, and that'll have a certain shape to it, which is based on what the distribution of charges is here. If I have, instead of a shape like this, if I have a different shape, a tall skinny shape that is moving around like this, then I will have the same, I will also have a magnetic field, but it will look different. It will be a different pattern of magnetic field, different strength to different distance, for example. If I have the whole thing moving around, I'm going to have a big field from all these charges moving. If, though, when I add my energy, it is a single particle excitation, where I just get 2 particles that start spinning around, and most of it is just sitting there doing nothing, then I'm going to have a very different kind of magnetic field there. A different shape, different picture, it's going to look different. So what we do is we take this nucleus, we add energy to it, and then we watch that energy come out. So each of these different things will be different places on this chart of energy. When it comes out, I get the photons. But in atomic physics, what I was really interested in with my photons coming out is how much energy they have. That's what I was measuring. What color is the light that comes out? In nuclear physics, what I'm measuring is where they go. It matters to me how much energy they have, but I already know that stuff. If I'm doing modern nuclear physics, I want to know where they go. So if I have my nucleus in here, and I'm in some excited state, and it decays, the photons come out. And the photons come out, in the case we're talking about now, in kind of a cloverleafish pattern, like this. And for most of these excitations, this is the pattern of radiation that I have. What this means, what this picture means, is I've got my nucleus sitting there, and if I'm sitting out here, and I'm looking this way, I don't see very many photons come out. If I'm over here, I see a lot of them come out. It's just a pattern where the photons come out. They tend to come out here and here, and they really don't come out on the corners at all. So that's my basic radiation pattern that comes out from my decaying nucleus. What I'll say, before I go too far, is that The excitations I'm talking about are elastic excitations. What that means is it's a billiard ball picture. The other word for it is Coulomb excitation. Coulomb is the word, it's a guy's name, but it refers to the electromagnetic force of the two charges. So this is a billiard ball picture. I have one nucleus that comes in, crashes into another nucleus, and bounces off. They don't break, there's no fission, there's no fusion, nothing shatters, not really changing anything about it. I'm just adding energy to it. And the way I add energy is that plain vanilla billiard ball type of picture. Nothing in the nucleus is really changing. I can go to higher energies and start breaking the nucleus and study different kinds of things. But in this case, I'm really just talking about this billiard ball picture. I add energy, it comes back. I had the same nucleus state I started out. So with that, I'm able to measure this magnetic field, and this magnetic field, and where it is, tells me what the shape of the nucleus is. So now, how do I do it? I've got to go through each of these steps. I've got to get a nucleus, I've got to add the energy. Getting the nucleus means I just have to find whatever it is I want to study. Usually I dig it up out of the ground, or I make it in a reactor, I separate it out, and then I have these pure isotopes of some nucleus, and I can study it. Then I have it. Is getting them, finding them, sourcing them, is a black art in a sense. I mean, it's really hard to figure out what it is you need to get and how to actually acquire it. And that's usually somebody else's job. You go to an accelerator facility, and it's not physicists that are doing it, it's some other branch of something. Most of them we actually get from the military one way or another because they have reactors doing other things, so they're studying something else. A lot of the time that I was doing my research, they all came from Russia, because Russia was the only one left that had a reactor that was still doing these kinds of things, and we had turned all our old reactors off. So you get these little precious vials of a tiny amount of the thing that you want to study, and then you study because you're looking for all different kinds.
You keep saying get a nucleus.
Right.
How, in real life, even when you're doing some kind of experiment, how much material are you talking about?
It's
thousands or hundreds of thousands or millions of nuclei?
It's way more than millions. It's how much you need is how much you need to be able to work with physically to actually put the thing together. So if I'm going to make a target out of this stuff, I need just enough dust to be able to make a little sprinkling of it on top, or I need enough to put in my vial to heat up to boil them off to accelerate. But the limit there is what you need to work with mechanically as a person or with whatever tools you happen to have. So this is a particle accelerator, a nuclear accelerator. This was at Yale. This is where half my research was here. This is the Yale Wright Nuclear Structure Lab. This was in operation from the mid-'80s through, I think, 2011. They turned it off and shut it down in favor of bigger machines. This is just a gigantic tank. A little bit of scale here. You can see a trough. This thing goes inside that building. That building is underground because there are radioactive things that come off as you're doing the accelerator physics, as you're accelerating the particles, and you need to absorb them, keep them from getting out into the public and scaring people. And the cheapest absorber in the world is dirt. So you usually either bury these things in the ground, or in a lot of cases, you build the thing and then you just throw a ton of dirt on top of it. And it looks like a mound, or it just looks like a big kind of dirt berm, and that's where the reactor or the accelerator is inside there, because dirt is really cheap. So what this tank is over on this end, I have a little machine there that boils off the nuclei that I need. And it's just a huge electric field. It's a Van de Graaff accelerator, if that means anything, like Van de Graaff generator, if you turn the crank and it makes your hair stand up. It just creates an electric field. And I take my nucleus, which starts out as an atom, somehow I just knock off a couple of electrons so it has a charge, I put it in the electric field, and it races from one end to the other. And that's really all it is. I can steer it with magnets because I have a moving charge, so I just put a magnet there and I can bend it. And it goes from one end of this tank to the other end of this tank, shoots out the back end, and then I can steer the thing. The tank has to be empty of anything else, because if I start making things go fast, if there's stuff in that tank for the nuclei to crash into, they're going to crash and they're not going to come out. Something else will happen. So I have to get it really empty. I also need it empty because in order to get enough of an electric field, I need a huge electric field. I need a lot of difference in voltage. When I say electric field, I mean a voltage difference. So there's hundreds of thousands, millions of volts of difference between one end of this tank and the other end. It's that millions of volts that makes the electron want to fly from one end to the other and gets it going fast enough to be able to bounce off with enough energy to be able to get me into one of these excited states. So I need all that voltage. If I have a big difference in voltage, electricity really, really wants to go from one to the other. It's that, danger, high voltage power lines don't get close. The electricity wants to go.